Okay, so let me move to the frequency response of MOS amplifier circuits. So as we have observed the amplifier just like a black box, and we have realized this amplifier using MOS based devices. And as of now, we have described three types of topology typically: the common source, common gate, common drain, and obviously the common source, common gate cascade kind of amplifier. And there you have seen the related advantages and the disadvantages coming out of these different types of topologies. Now, so we have not considered the effect of any capacitors. You understand that, okay, whenever you have also studied the BJT based amplifier circuits, there also you have seen that there are few which are externally connected, like the coupling capacitors, the bypass capacitors, all these things. And apart from that, you are designing or you have used this BJT, you have different types of parasitic capacitors, internal capacitors you have, right? Here also you have different types of capacitors, and whenever you consider those capacitors count, obviously the gain that you are getting, this gain is not independent of the frequency. Now what is the essence? So whenever we are designing any amplifier, so there are a few attributes of any amplifier, as you know. You would like to increase the gain as much. Second one is the stability. Your amplifier should be stable one. Third one is obviously what else? The voltage swing. And obviously the input and the output impedances. Input and output or resistance to be specific, because as of now we have not considered the frequency sensitive elements. What else? What else? Gain, stability, voltage swing, impedance. What else? What do you expect apart from these factors? Obviously the speed of the amplifier. That means what? Suppose you have provided some input like a naught cos omega naught t, when omega naught is the corresponding, or omega naught is equal to twice by f naught is the frequency, omega naught is angular frequency, and suppose you are increasing or you are changing this frequency value. Suppose you start with some few hertz, from hertz, suppose say hundreds of megahertz. Okay, hertz to megahertz. Then whether the performance amplifier remains odd or different. That is the thing. And for which you have to consider the effect of different capacitors which are already there internally inside this MOS device. Right. And in this particular unit, we will definitely look into this. Once again, let's take a look at the structure of NMOS over here. Yeah. So NMOS is fabricated on P-type substrate. Then you have this N plus region as source and effectively, and the gate is there, and in between this you have the oxide layer, oxide capacitors. Right? Now, during the drain current, hopefully you can remember that in that expression you have one term which is known as the C-ox. What was that? If you can remember the expression of the drain current of MOS device operating either in the saturation or in the linear region, ID is equal to some movement C-ox, WIL and something. What is that C-ox? That is oxide capacitance per unit area. That means whenever you have some gate over here, which is nothing but a polysilicon layer over there, and apart from that you have some P-type substrate, a semiconductor. So you can always consider this this polysilicon as conductive material. And here you have P-type substrate, a semiconductor, which is also finite conductivity. So you have two conductors, and in between these two conductors some silicon dioxide, the insulator, and this gives the notion of a capacitance. Discussing the device physics of a MOS of this MOS transistor, we have started our discussion from that perspective only. But a capacitor. And what is the value of this capacitor? We have assumed that, okay, C oxide capacitor per unit area. That means from here from gate to substrate, you can consider that this capacitor or this corresponding capacitance is distributed. You don't have any lumped capacitance. This is distributed. Now, for the sake of analysis, what we are now decomposing this capacitor into two different values, two different capacitors. One is the capacitance which is there between the gate and source, and the second one is between the gate and the drain. Right? And apart from that, you have a reverse bias PN junction over here, at least not forward biased. This N plus P, drain to substrate and drain to body and the source to body. So this gives rise to another two capacitors. So altogether you have four capacitors in general. One is between gate to source, second one is between gate to drain, third one is between source to body, and the fourth to body. You have four capacitors. So whenever you have some MOS devices, so obviously you have to consider all these four capacitors: CGS, CGD, CSB. And now you have to consider all these four capacitors in case the two terminals are held at two different potentials. For example, if your source and the body they are held at two different potentials, then you have to consider this capacitor, the CSB. If the potential at the drain and the body, if they are held at two different values, then you have to consider that particular capacitors. In case both the source and the body they are connected to the same potential. As you know, for NMOS, typically the body is connected to ground, and suppose it's a common source is directly connected to ground. So both source and body, source and bulb, both of them are connected to the ground potential. Right. So in that case, what happens? So both of these two terminals they are having the same potential over here and over here. In that case, the effect of these capacitors will not be there. So in general, you have to start with these four capacitors, and then as the need arises, you can simply get rid of one capacitors. That is the one way of analyzing this kind of amplifier circuits in the frequency domain, and hopefully that part we have already discussed in our the Miller effect. Sometimes you know that some capacitor which is connected between the input or some connected between the input and the output, which is acting as a feedback element. What we are doing for the sake of analysis, we have decomposed this into two different impedances. One is between this terminal, input terminal to the reference, and second one is between the output terminal and the reference. So I am not going into the details of this because this has been already discussed in the previous semester in electronic circuits course. So suppose so that is the impedance. So that impedance is connected between the input terminal, input port, and the output port. So V1 corresponding to the voltage available at the port 1 or the input port, and V2 is the voltage available at the port 2 or the output port, and this is the reference line. And that impedance Z is connected between the port 1 and the port 2. Suppose we are interested in finding out the effective value of this Z between these two terms. That you already noticed that value is given by Z upon 1 minus A, where A is the gain of the amplifier. Similarly, the output side, that is nothing but Z upon 1 minus A inverse. Now typically if A is large, for an amplifier A is large, so A inverse is small. So in that case the Z effective out is almost equal to Z. However, if A is large enough and negative for common source amplifier, as you know, in that case the effective value of this impedance will be, what will be the effective value of the impedance? Reduced. Because Z effective is equal to Z upon 1 minus A, and A is large. Suppose A is equal to minus 10, minus 20. So Z effective in will be less as compared to Z. And as you know, this is the relation between the impedance and the capacitance of any capacitor. Z is equal to 1 upon SC. So therefore, the effective value of this capacitor, the input side is given by 1 minus A times C, and the effective value of the capacitor, the output side is given by 1 minus A inverse times C. That concept we can simply borrow from your electronic circuits course. Okay, so let's start with a simple common source amplifier. A common source amplifier which is driven by a resistive kind of load, RD. Right? So here you have a common source amplifier by virtue of NMOS device. We have just designed this one, and the source is connected to the ground, and you have a typical register for the timing. Let's assume that you have a discrete register RD in place, and gradually we will replace this RD by means of some other elements. As you know, RD can be realized by means of some load or some direct connected load, right? So once you have this MOS, so consider 4 such capacitors. One is between the gate and the source, this one. Second one is between the gate and the drain, this one. Third one is between the source and the body, this one. And fourth one is between the drain and the body, this one. Now for NMOS, typically this body terminal is connected to ground. So therefore, and here also the source is connected to ground, right? So therefore, between source to body, if I have this capacitor CSB, so both of these two terminals, they are having the same potential. Here also ground, here also ground, source and ground. So therefore, the effect of these capacitors will not be there. For capacitor CGS, will it be there? Yes, because source is at ground and gate is obviously having that potential which is applied to the input side. Similarly, this particular capacitor CGD, which is connected between the input side and output side, and none of these voltages are the same. And for CDB, this is the output terminal and this is your body potential, that means the ground potential. Right? So out of these 4 capacitors, you can simply neglect the C for this kind of configuration. Can you tell me, out of this, so now we have only 3 left, CGS, CGD and CDB. Now out of this, can you tell me, is there any capacitor which is experiencing effect? Yes or no? Yes. Which one? CGD. Because CGD is connected between the gate and the drain, and gate is acting as the input terminal for a common source, and drain is acting as the output terminal for the common source. So therefore, CGD is experiencing the Miller effect. Right? Okay. So scenario for a common source amplifier with a resistive load, simple resistive load RT. Now you can also realize this one by virtue of some current source load. That means this RD is replaced by means of some current source device, and that is nothing but a PMOS here. So that you can simply neglect the corresponding body effect. Right? So now what you have for M1, you have once again these 4 capacitors. Initially, CGS1, CGD1, CDB1 and CSB1. And the effect of the CSB1 is absent. And M2 is acting as a current source load, for which the gate is having some potential sub say VB, and source is having the potential equal to VDD, that is the supply, and the drain of this MOS M2 is the output terminal. These 2 drains are shorted together. Right? And you understand that for this one, for M1, the body is connected to ground, and for M2, this is connected to VDD. Right? Now you tell me, out of these two, which of these two, out of these 2 MOS, which one is experiencing body effect? Is there any MOS body effect? None of them. Because for M1, the source is connected to ground and the body is also connected to ground. So C is the VSB, that is equal to 0. Similarly, for the MOS M2, source is connected to VDD and the body is always connected to VDD. For M2, once again you have 4 capacitors, CGS2, CGD2, CSB2 and CDB2. Right? Now out of these 4 capacitors, can you simplify any of them? These 4, CDB2, CSB2 and CGS2. It has already been shown that you can neglect CGS2 and CSB2. Why? Because Yes, so for MOS M2, source 2 is connected to VDD, which is equivalent to AC ground. Gate 2 is connected to VB, which is also equivalent to AC ground. So therefore, both of these two terminals, CG2 and CS2, because whenever we consider the effect of the capacitors in the frequency domain, so obviously we will perform the AC analysis, right? Because for DC, this capacitor will act as an open circuit. So you have to perform the DC analysis, AC analysis, and for which both of these two terminals, this terminal for MOS2 and the source terminal for MOS2, both of them are connected to AC ground. So therefore, CGS2 is completely absent because both this CG2 and CS2 they are connected to the AC ground. What about the CSB2? Source is connected to VDD, that means AC ground. Body is also connected to VDD for PMOS. You cannot consider the CSB2 as well, right? So out of four different capacitors over there, CGS2, CSB2, CGT2 and CDB2, you can get rid of CGS2 and CSB2. Then what you have altogether how many terminals in this particular circuit, in the second circuit, how many terminals are there? Once you have a terminal, once you have a node, that particular node corresponds to a particular time constant. You have some associated resistance, you have some associated capacitance, right? How many signal nodes are present? How many signal nodes are present? V in and V out. So you have this one, this is one node, right? And this is another node. This is always connected to ground, no signal. Source 1, gate 2 connected to AC ground, source 2 connected to AC ground, and this is the common terminal, right? So you have this is one node over here which can contribute to some time constant, some RC time constant, and here this particular node also contribute to some time constant, and accordingly we have to find out what is the effective resistance over there and what is the effective capacitance over there at this particular node. Similarly, what is the effective resistance over here and what is the effective capacitance over here, and if you just simplify both of them, then you can find out some approximate expression for the input time constant as well as for the output time constant. And once you have the expression for the corresponding time constant, RC time constant, then approximately you can find out what will be the expression for the transfer function, H of this. That is the approximate calculation, and if you go for the actual calculation, then you have to simply draw the small signal model and you have to apply the KCL and KVL and find out the expression. Okay, so you have here one is input node, that is a G1, and output node that is equal to D1 or D2 you can call it, because D1 and D2 they are connected together. We have started with 4 plus 4, 8 capacitors. Out of them, 3 are redundant. We are left with 5, right? CGS1, CDB1, CGD1, CGD2, and CDB2. Out of them, is there any capacitor which is experiencing Miller effect? CGD1. So what you have to do, you have to decompose this CGD1 into two capacitors. One connected between this G1 and ground, and second one connected between the D1 and ground. So what is the effective capacitor from connected between the here and ground, D1 and ground? This is nothing but close to CGD1, right? This, if A is large, then in that case, this you can consider this A inverse to be very small. For common source, negative. So A is large, A inverse can be considered to be almost equal to 0. So now here at gate 1, you have 2 capacitors. One is CGS1 connected between the ground, and you have another capacitor that is a component of this CGD1 connected between the gate 1 and the ground. decomposed CGD1 connected between the gate and the ground. What is that? 1 minus A times CGD1. So these two capacitors are there in parallel. So what is effective capacitance? Nothing but a summation. And here at the one you have how many? You have 3 capacitors.
C dash.
Yes. 3 capacitors. One is CDB1, drain 1 to ground. Second one is CDB2, drain 2 to ground. Drain 1 and drain 2 they are connected together. And third one is CGD2 connected between the 2 and AC ground. So instead of having these 3 capacitors separately, CDB1, CDB2 and CGD2, you can simply replace all these 3 capacitors by means of a single capacitor. What is that? It is C dash, which is connected between the D1 or D2 to ground. C dash is one capacitor, and obviously you have to consider the effect of this CGD1. Right, that is actually almost close to equal to CGD1. Is it okay? Is it clear? Okay, so now let's have a look at the common drain amplifier. For common drain amplifier, as you understand, this MOS M1 is acting as the amplifying device. Actually, there is no amplification. It is acting as a buffer, and the resistance over there is represented by another MOS, that is M2. Right. So therefore, since you have introduced two MOS devices over there, M1 and M2, so you have to consider the effect of the corresponding capacitor. So altogether you have 4 plus 4. One MOS, you have to consider the 4 capacitors, CGS1 or CGS, CGD, CSB and CDB, 4 capacitors for every MOS. Then for MOS1 M1, you have CGS1, CGD1, CDB1 and CSB1. For a common source amplifier, you have seen that this CSB1 you can neglect. For common source amplifier, you can neglect CSB1 because source was connected to. But for common drain, you cannot. For common drain, you cannot neglect or you cannot get rid of CSB1. Right? Why not? Because for common drain, source is your output terminal. So source is a signal node. You cannot get rid of that. So here you have some signal variation, and here so the body is connected to AC ground. But for common drain, you can get rid of CDB1 because drain is connected to VDD, which is equivalent to AC ground. Body is already connected to AC ground. So see this CDB1 you can simply neglect for common drain. Right? So out of 4, you can simply get rid of CDB1 for common drain amplifier. What about this one, this load MOS, which is acting as a load device? For M2, since the source is connected to AC ground, so you can simply ignore the CSB2. And for CGS2, this gate is connected to some constant voltage VB, which is equivalent to AC ground, and the source is connected to DC ground, you can say. So therefore, CGS2 you can simply neglect. So CGS2 and CSB2, these are absent. Right? Once again, how many signal node you can consider? You can consider 2 signal nodes. One is obviously this one, this G1, and second one is obviously your S1 or D2. Same thing, because D2 and S1 they are connected. And at terminal D2 or C1, you have different capacitors which are connected in parallel. So you can consider the effective capacitor as C dash, which is nothing but this CSB1, which is connected between the source one and the body one, this CSB1. Plus you have this CDB2, which is connected between the drain 2 and the body 2, and obviously this CGD2, which is connected between the drain 2 and the gate 2. So instead of having these 3 capacitors, this CDB2, CSB1 and CGD2 separately, you can consider a single capacitor which is equal to C. Right? And obviously at the input side, what you can consider at the right, you have this particular capacitor CGD1 connected between the gate and the drain one. Is there any capacitor which is experiencing Miller effect? Huh? CGS 1 or 2? CGS 2 is absent, so CGS 1, which is there between the gate 1 and the source 1. So therefore you have to decompose this CGS 1, the component of CGS 1 between the gate 1 and the ground, and the component of CGS 1 between the source 1 and the ground. Right? Okay. And finally, you have a common gate amplifier. As you understand, the input is applied at the source terminal. This is the input signal which is applied at the source terminal through some resistance over here. And for the sake of simplicity, we have considered only one discrete resistor in the form of, say, RD. Then, since you have this particular MOS, so you have to consider 4 different capacitors. One is CGS1, second one is CGD1, then you have the CDB1, and finally CSB1. Okay? Out of that 4 capacitors, neglect any of them? Can you neglect any of them? CGS1, CGD1, CSB1, and CDB1? Yes or no? Can you neglect any of them out of this for common gate amplifier? Can you neglect any one of them? Remember, source 1 is connected to input, or as a source, they have only one MOS. Source is connected to the input, drain is connected to the output, right? And gate is having some voltage VB, which is equivalent to AC ground. So therefore, for CGS1, this is your one signal node, this is the ground terminal. For CGD1, this is the another signal node, that is the output signal, is the ground. For CDB1, this is the output signal node, this one is the ground, and CDB1, this is the input signal node, and this is the ground. So therefore, if you consider any of these capacitors, you find that both of these two terminals, either of them is connected to the signal node and the other one is connected to the ground. So you cannot neglect any one of them. Right? Is there any capacitor which is similar effect? Huh? CGT1. Is there any? So Miller effect will be there when one for any capacitor, if one terminal is connected to input, the other terminal is connected to output. But this time their input is what? Input is the source and output is the drain. Do you have any capacitor connected between the source and? So for common gate, you don't have any Miller effect. None of the capacitors, they are experiencing Miller effect. So you can expect, so based on this discussion for the last 10 minutes or so, 15 minutes or so, you can expect a say MCQ question like this. Now that is the synthesis part, no? The question is something like, question goes something like this. Out of the following options, for which case you don't have the Miller effect? Common source, common gate, common drain, cascode.